Yes, class. Am I audible? Good evening, all.
Good evening, ma'am.
So we had completed till this topic, width of central maxima. So let's quickly finish with this lesson so that we can start with dual nature of matter. And you also have your test today of interference. So at least let's start with this so that you can be prepared, you can get time for this. And then dual nature of matter and radiation is a small topic. It has only two components, not two topics. Now, intensity distribution curve we had seen when we were discussing interference. That time we had discussed intensity distribution curve, if you all remember. So same thing, here also you will get intensity distribution curve. Remember, in case of interference, you had all the quantities whichever were present. Intensity didn't change. It means if you are getting fringes, different fringes are present. So what will happen? Just a second. Test in the last class only I had announced. No. Yes, others. I had announced that I'll take the test on the topic interference. Yes or no? Others.
Teacher, I was not present last class.
Okay, you were not present in the last class. Okay, Fatima. So interference test is there today. So see, width of central maxima. This we had discussed. Now intensity distribution curve is there.
Ma'am, is it possible if you can keep the test on the next class?
Next class. Okay, fine then. So next, what's the date then?
Tuesday.
Tuesday, no? Next is Tuesday. What will be the date for Tuesday? This is today is 14th. No, 15th, 16th, 17th is it. So 21st, 22nd. 22nd, okay. So 22nd, I'll take the test then. Fine. So now I'll write on the WhatsApp also. So if all those who have not attended, those can. So I think the last test was on 14th. Today is 17th. Next test will be on 22nd. Some papers are unchecked. No, some papers of yours are left unchecked. That also submit. I'll show the score today. Anyways, I'll have postponed the test. 22nd, I'll take the test of this interference. Now, C class, intensity distribution curve. So see, for intensity distribution curve, no, suppose you have for minima, you have the path difference as n lambda. Path difference is n lambda. Now see, if path difference is n lambda, so if you put the value of n, as you put the value of n, you get the first minima. So that is lambda directly as soon as you put it. Now, if you take n as 2, so that will become what? 2 lambda. Like this, you'll have all the values that are present. Similarly, 3, as you put n as 3, you get 3 lambda. N as 4, 4 lambda. N as 5, 5 lambda. And so on. Right? Whatever value of n you will choose, exactly lambda you will obtain. That will be the path difference. So you have minima for those values. Same thing, maxima's formula is what? 2n plus 1 lambda by 2. So first maxima will be what? If you put n as 1, you get 3 lambda by 2. If you put n as 2, you get 5 lambda by 2. So all the odd multiples you will get. If you put n as 3, you will get 7 lambda by 2. Like this and so on, it will be present. So what is happening to the intensity? It decreases. And now I'll show you the graph. So see the difference, the graph that we had seen, intensity distribution curve that we had seen in case of interference pattern. For coherent sources, the interference pattern intensity remained constant because the phase difference didn't change. So intensity didn't change with the phase difference. So it remained constant. Right now, what is happening? Intensity is gradually decreasing. So what is the physical meaning of this? This actually means that even if you take that same experiment that I was referring in case of interference, same that comb example that you take, if you take comb and between the bristles of the comb, you just leave one of the bristles, it means just one slit and cover the rest of portion. And then you project in laser light. So what will happen at the center, no, on the wall, on the screen, you'll get very, very bright central maxima. On the side, there will be slight darkness, and on the side of it, there will be slight redness. Then again, slight redness, and it will keep on decreasing. Now, how do we get the value of intensity as I by 21, I by 61, and so on? This is according to polarization. Brewster's law is there. Some of these topics are there. Now, these topics have been deleted. So, you all don't need to worry about it. This topic has already been deleted. So just remember the values that if by chance intensity distribution curve comes for you. So for intensity distribution curve, you'll have to choose the values I by 21, I by 61, and all these values. These will remain fixed. So do not change these values by yourselves or do not try to calculate these values. Why? Because see, simply intensity is decreasing. This fact you have to know. You have to understand this fact that yes, intensity is decreasing. Now, intensity is decreasing by 21 times, by 61 times. This value you have to remember. Now, why do you have to remember this value? As I've told you, polarization, Brewster's law provide all these values. So no need to go into the details of it. But one difference that you have to notice, the difference in the reduction in the intensity. All right, so intensity gradually decreases. This is about the intensity distribution curve. So again, I'm repeating. For interference, the intensity of the fringes that are present, dark fringe and the bright fringe, it remains constant for coherent sources and it is totally independent of phase difference for non-coherent sources. In case of diffraction, the intensity gradually it keeps on decreasing. So when you'll perform the real experiment, you will observe very slight spotting redness that is present or any color of light which you have taken because intensity is so less. All right. So do one thing, class, note it till here. Then one or two things are left to be discussed. Then we'll discuss it here. Now, yes, C class. See, destructive and constructive interference I have discussed with you, no? When either the crest coincides with the trough of another wave or the trough of one wave coincides with the crest of another wave. So when such superpositions occur, that is known as destructive interference, because this decreases the amplitude, not amplitude, resultant amplitude, the intensity, resultant intensity. And constructive superposition was what? When crest coincides with crest and trough coincides with trough. So that results into a greater crest and a greater trough below the line, like this. So see, a type of question that you get is, see, for all these values, n lambda, like 1 lambda, 2 lambda, 3 lambda, all these values, we are obtaining a minima only. And for all these values, so that's 3 lambda by 2, 5 lambda by 2, lambda by 2 itself, because if you put this as 0, you'll get lambda by 2, all these values, you get a maxima. So how can you prove that, yes, they are, this will lead you towards minima, this will lead to you towards maxima? So see, so question is, why the path difference of lambda results in minima? So very simple answer it has. See, class, this is point A, this is point B, let's say. Now, the entire slit width is small a. I have divided the slit into two parts, fine? This is A by 2, this is A by 2, right? Now see, when the waves will come from A, they will get bent because diffraction will occur. So from this upper half that is present, this one, what will happen to the waves? In this upper half, waves will come, and in this lower half also waves will come. So half portion will come from above, half portion will come below. So what will happen? They'll superimpose destructively, right? Because one is having a crest, another one will be having a trough. That will only complete one complete wavelength. No. So since they'll superimpose destructively, that will decrease everything. Intensity, it will decrease, amplitude, it will decrease. So hence, that's why we say that both of these, when they'll coincide or superimpose destructively, this results in minima. I've written all the points as well. See, path difference between waves coming from A is lambda. Dividing slit into two equal parts. Path difference between waves from upper half and lower half have a path difference of lambda by 2. See, from the upper half, this is a one complete wavelength, as I was saying, one complete wavelength is lambda. So this half portion, when the slit is A by 2, that will become lambda by 2. Entire is lambda, half of will become lambda by 2, lambda by 2. And lambda by 2 is the condition of what? Destructive interference only. So that's why this results into minima, because of destructive interference. So waves superimpose destructively, resulting in minima. Same thing, if the path difference is 3 lambda by 2. So how it results into a maxima? So same thing, take 2 points AB or at the edges of the slit, take the slit width as small a. Divide this into 3 parts. Fine, 1 part, 2 part, and 3 part. So this becomes A by 3, this becomes A by 3, this becomes A by 3. 3 parts I have divided. So waves, when the waves will come from this part, A part, B part, see, all these are there. So they'll have a difference of 3 lambda by 2 now. Now see, from the above two parts, means from this first part and from this second part, they'll still have a path difference of lambda by 2, right? Because this we have discussed. From two parts, it will have lambda by 2 because one entire was lambda. Half gave you lambda by 2, lambda by 2. Now, if this entire is lambda by 2, so it means they have superimposed destructively. But what about this? The part that is left. This is something extra. This is additional to the waves that are present. So that's why this results into a greater amplitude. It's like these two have cancelled each other and one part is remaining. So this is extra, which is increasing the value. So see, I've written it also. Waves coming from point A and B will have a path difference of 3 lambda by 2. And it says that divide the slit into 3 equal parts. So waves coming from first 2 parts will have a path difference of λ/2 like the previous question. So they'll superimpose destructively. But see, third wave from this one, wave from the third slit will contribute to the maximum. So see, when you will have even multiples, for even multiples, what will happen? Everything will get divided into equal parts. So all the wavelengths will get divided. So it will always superimpose destructively because you'll get the values as such. No, λ/2 for one, for two, you'll get lambda. Then like this, it will keep on moving. So that will coincide with the values of destructive interference. So see in your question, this will come directly like this only. But whatever question comes, whatever value they choose, instead of lambda, even if they give you 3 lambda, 4 lambda, something like this, write the answer exactly the same. Fine, write the answer exactly this. So this is because of destructive and constructive interference. Note this down. Then one last topic is left from wave optics. That is the difference between interference and diffraction. Because this question has come in your board exam once, so we'll discuss it.
So, teacher, can you scroll up, please? Thank you, teacher.
Class, now the last topic, as I was saying, that is the difference between interference and diffraction. See, basic points I'll discuss with you. Rest of the things you can also write it down. Just in case a 5-marker question comes in your exam to write about the differences, though it should not come in your 5 markers, but still. See, first major important difference is that interference, no, this occurs because of superposition of light waves from two coherent sources. Fine. Two coherent sources are there, they superimpose, light waves superimpose, and it results into interference, and the bright fringes and so on, they form. In case of diffraction, so superposition of secondary wavelets occur. Fine, superposition of secondary wavelets result into, from the same wavefront, result into diffraction pattern. So it is actually from the, it is superposition of secondary wavelets from the same wavefront. And in case of interference, what do you have? You have proper two coherent sources that are emitting light waves. This is the basic difference. Basic difference you can see, or the definition in your answer. The first point, whenever in any subject comes to differentiate, first point usually write the definition, because if there is a difference and if the question is there, it means there has to be certain difference. Definitely, that's why the question has come. And if there is a question, if there's a difference, firstly it will be the difference in the definition. If very slight difference is there, then don't write the definition. But here these two are independent topics. Then second point, bright fringes, as we had seen the intensity distribution curve also, bright fringes have the same intensity. You perform the experiment on YouTube, also search it. I think from this class only Huzaifa is present today. Huzaifa Ahmed. Huzaifa was, or Hamza? Who was having the experiment on YDSC, Hamza or Huzaifa? I think one of you was having the investigative project activity, no? Okay, Hamza. Okay, I'm sorry, Huzaifa. Hamza. So Hamza, you must have gone through the videos, no, also on YouTube. Did you see the experiments on YDSC? Experiments also you must have seen? Okay. So experiments that were done, DIY experiments basically, that you can perform at home. So not the actual apparatus is required. So even all of you also, if you go through the experiments of YDSC, you will notice that the fringes that are formed are all bright. Bright fringes appear to you bright, and all the dark fringes appear to you as dark. Fine. So here as well, here in case of diffraction patterns, you won't observe the same thing. For diffraction pattern, you won't observe the same thing. Intensity decreases, even though through the intensity distribution curve also we had seen this fact. Intensity decreases, it means center, no, exactly at the center, you will observe very bright fringe. On the side, darkness, definitely, minima, which we say. Then decrement, a little decrement in intensity. Then a little more decrement in the intensity. Similarly. At the end, it will be very slight, just shade that you will be able to observe. So this is the second difference. Then regarding the fringe width, you can add on the difference. Fringes have the same width. If this is the angle that is subtended, angular fringe width is there, or linear separation is there, or normal fringe width is there. So for the bright fringes, for all the fringes, not the bright, not the dark, because fringe width remain the same. So for all the fringes, you will observe that the fringes have the same width. All the fringes have the same width. This you will observe. Fine. All the fringes have the same width. In case of diffraction, fringes can have variable width from the central maxima. You can notice that the central maxima is having the maximum value. But as soon as this comes for the fact of the other fringes that are present beside the central maxima, intensity decreases and width also changes. This also you can observe. One more point. One very important point is, when you will perform the interference experiment, or if you observe Young's double slit experiment that is present, you will observe that bright fringes you are able to differentiate. You don't need to make any effort, or you don't need to make the room totally dark just to observe whether the fringes, there's a difference between the dark fringe and the bright. Yes, this is a little brighter, this is appearing shiny, so this is bright one, this is a little dull, I think, so I think this is the dark one. No, not like this. There's such a good contrast between the fringes, no, that when you perform interference, in the interference experiments, you will be able to clearly observe the contrast between the bright and the dark fringes. You will be able to, your eyes will easily be able to segregate it. When it is the case of diffraction, there the contrast is not good. Fadings are there at the edges, slight fadings. You're not able to easily see the perfect difference between the maxima and minima. Maxima and minima. You have to identify by yourself. Yes, this is appearing bright. This is it. Especially in the cases in the regions where intensity decreasing is much more, then more you have to observe it because of the poor contrast. So all these points I have written it already, I think. So first point, definition. Second point, bright fringes have the same intensity. Intensity decreases in case of diffraction. Third point, all fringes have same width. Fringe width varies. And last point is good contrast between dark and bright fringes. And here you have poor contrast between maxima and minima. Now, C class. Note this down. One more thing. If it comes in your exam and it's for 3 marks, I think this much is enough. By any chance, if you get this question for a proper 5-mark question, no, then add the intensity distribution curve as well. That will add on your points. And that will add on your points. Note these differences. Chapter is over. We'll start with modern physics. Note it down. Any doubts you have, let me know. Just text done in the chat column when all of you have completed. And if you have any doubts from wave optics, do let me know. Okay, so Krishna and Sarah have done. What about others? Written till here or not? Okay, okay, all have done. So do one thing. Let's do one thing. I'll give you 5 minutes because we have to start with a new chapter now, new unit, in fact. So everything is different totally from what we have studied. Take a break of 5 minutes. Revise the lesson. If you have any doubts, pending doubts from the lesson, let me know. Papers, your marks also I'll show you at the end. Today, since the test is not there, so now I'll straight away start from the new chapter because test is on Tuesday, so I'll start with the new chapter, dual nature of matter and radiation. So it's 7:20 here in India. At 25, I'll start with the class then. Till the time, if you have any doubts, you can ask. Otherwise, just take a break of 5 minutes. Yes, class. So I think 5 minutes have gone already. So let's start with dual nature of matter and radiation. See, first thing that comes, no, the concept here. That is a concept that we had discussed when we were having the initial classes of class 12. Remember, we were discussing the structure, how free electrons are present, how electrons get transferred, and this is the transfer of electrons that occurs and not the protons that occur, and all these structures we were studying. So one very important thing that we had studied was concept of free electrons. This was a very important concept that we had discussed, free electrons. So free electrons are what? Basically in your, let's say this is a wire. Let me try it here. So this is a very small part of the wire that I've drawn. This does not mean that the wire is very short. It means from the wire, no. Let's say this is the wire. So just this part I have taken, small part, I have enlarged it and I have shown. Now what all things are present? There are free electrons that are present. There are some positive ions that are also present, some protons present, some positive charges present, positive ions present, negative ions, all these are present. Now, when I say the electrons are free, so it does not mean that they are just kept on the surface and you can just extract the electron. No, free electron means that electrons definitely are free. When we add this term free in our the definition, whenever we add this term, this means that free electrons are the electrons that can become free or that can become available for conduction to occur. That is what is meant by that is what is meant by free electrons. So in case of free electrons, what can happen? The electron, when they are provided certain conditions, every electron has its conditions. If you fulfill those conditions, then the electron can become free. It will be available that yes, I'm available for conduction of electricity to occur. Now, what are those conditions? Specific wavelength is required, specific amount of frequency is required, specific amount of energy is required. So whenever a light ray falls on this electron, any electron, and it has the specific light frequency wavelength that is required by this electron, then this electron becomes available for conduction. Then only we say this electron is a free electron. Otherwise, this is not that electrons are just kept on the wire or just kept as it is within the wire, and whichever electron you wish, you can take it out. No. Free electrons become free. So these conditions, where you have certain amount of energy that is required, where you have certain frequency, where you have certain threshold wavelengths to be crossed, that minimum amount of energy that is required by electron, that is known as work function. Class, one more thing. I have certain handwritten notes for this, which are very good for you from your board perspective as well. So these electrons and all these part that I have free electrons, all the topic de Broglie, photoelectric effect, everything that is present. So these I have already good notes with me. So I'll not write everything because this is a very theoretical chapter as well. Photoelectric effect has equations, but most of the things are very much theoretical. And class, modern physics, semiconductors, both these units. Class, this is a very scoring part that you can achieve, especially dual nature of matter and radiation, atoms, nuclei. Now maximum parts have been deleted that were difficult. Now only easy portions are available. So please do not never leave this lesson. This is a score booster lesson for you. Just write the definition. Whatever we'll study, together, that will only come. This is very obvious what type of questions will come. All right. So please do not leave from the second book, Modern Physics and Semiconductors. Even for students who are not very good at physics, this lesson will not require so much of your knowledge of physics. I'm telling you, chapter 4 till chapter 4, your current, electricity, magnetism, magnetics and matter you have, and your electrostat, there requires the concept. Concept is very important, because if you do not understand the concept, you will not be able to solve numericals till a certain time. Modern physics, no, this is very certain. If I'm saying photoelectric definition, then photoelectric's definition only will come. There will be no modification. Certain standard questions are fixed from Einstein's photoelectric equation, that only come in your exam. So again, I'm telling you, do not leave such chapters. They are very scoring chapters. Now, coming to the point, yes. So I'll write down few definitions which I think we can discuss in the class. Rest of the things, they'll be provided to you in the notes. So this is known as work function. So again, work function means what? The minimum amount of energy. Amount of energy required by an electron. Required by an electron to just escape from the metal surface. This is called work function. Usually this work function is denoted by this sign phi. Now see, these conditions that are satisfied, or how the electron's emission occurs. The electron emissions can be of various types. The type of emission that can occur. Before things, see class, work function is actually amount of energy only. So usually we write it in terms of electron volt, 1 electron volt. But please remember this conversion. Yes, can anyone tell me how do we write what is the electronic charge that is present on an atom? What's the electronic charge that is present? Electronic charge.
1.6 into 10 to the power minus 19.
Minus 19. Fine. Good, Fatma. See, so same conversion. 1.6 into 10 to the power minus 19 joules. This is an important conversion because maximum answers will be satisfied by 1 electron volt only, just in case in anywhere you require electron volt to get converted into joules, because especially in photoelectric effect, the basic equation that is present, you will require this. In there, I think class 11's chemistry also, you have all these terms, photoelectric effect. I think in structure of atom, I don't know whether this is included now or not, but it was included earlier. Photoelectric effect and all these topics in your chemistry. So I think you must have an idea or not.
Yes, ma'am, it was there.
It was there, no? Okay. So then you must be having ideas. So now see the types of emissions that are possible, no? How this electron comes out. The electron is coming out of the metal surface. So it is firstly possible because, and this is known as thermionic emission. See, thermionic emission means when thermal energy is provided. Some amount of heat energy is provided to let the electron get separated and get detached from the wire's cross-section. That is known as thermionic energy. Then you have field energy. Field energy, you can say cold cathode energy, you can say. Cold cathode emission, you can say. So cathode rays tubes are required, high electric field rays are required to it. So basically, when a metal surface that is subjected to very high electric fields, high electric field, when I say it means 1,000 to 10,000 to 8,000 to a very huge number, 10 to the power 8, 10 to the power 9, such amount of electric fields whenever it is provided. Then because of electric field, the electrons can get emitted. So that is field emission. One, you have secondary emission. So see, secondary emission means when another electrons coincides with it, moving, this is because of moving electrons. When the moving electrons strike the metal surface, they can let this electron get released, right? They can get this electron to be released. So this is moving electrons. Other moving electrons can make this out. Last is photoelectric emission. So this means sunlight. Sunlight, now light. Photon basically means light. So when light rays emit the electron. Now, this is important. We'll study this only in detail. You have more or less two topics only in this. Class, in your previous year's paper, no, you will see, if anyone checks, you will see certain questions are based on Davison and Germer's experiment, and that we'll not be discussing. Because this is deleted this year. Now this is deleted. So even if you see that, no, Davison's and Germer's experiment, just ignore it, solve rest of the questions, because that is not a part of your syllabus. So coming to this now, expanding this photoelectric effect. So now we can conclude what? For photoelectric effect, we can conclude the fact that, see, whenever a light ray falls on an electron with a suitable frequency, suitable wavelength, it results into emission of electron. This phenomena is known as photoelectric emission. So photoelectric emission becomes what? Photoelectric effect, you can directly say, or photoelectric emission, you can say. See, for photoelectric phenomena that occurs, photoelectric effect that occurs, light of suitable frequency should strike the metal surface. Let me write it down. When light of suitable frequency strikes a metal surface. Strikes a metal surface, so electrons are emitted. Electrons are emitted from the metal surface or from it. This phenomena is called photoelectric effect. And the electrons that are ejected now, these electrons, these such type of electrons, these are known as photoelectrons. These are known as photoelectrons. Fine, so certain experiments were also done. Hertz gave his observation, Hallward Lenard's observation was there. Earlier, these were included in the syllabus. Now, these are not included in the syllabus. So, photoelectric effect, I am again repeating. This is what? Phenomena of emission of electrons from a metal surface when electromagnetic radiations of sufficiently high frequency, you can say, or suitable frequency is the best word to use it. That phenomena, whenever these light rays are incident on the metal surface, that is termed as photoelectric effect. And the light generated electrons, these are known as photoelectrons, not photons. Photons are different. These are photoelectrons. One experiment is also there that we will discuss. Note down these points, then we'll discuss it. See class, some experiments were done. That experiment till detail you don't need to study those details of the experiment, but certain conclusions you have to study. 3 to 4 graphs are there in your syllabus that you have to see. So see, for the experimental study of photoelectric effect, you must have heard of the scientist Millikan. R.A. Millikan was there. Millikan's oil drop experiment is also there to calculate the charge on a drop. So if you've heard of, he performed certain experiments with some more scientists. Leonard, no, he also gave the one of the observation with Hall watch. So same scientist. So they basically tried to explain the effect of intensity, potential, and frequency of incident radiation. These three things they tried to explain it. Now, C class, before we begin this, okay, let me explain you this already. Then in the meanwhile only, as soon as it will come, I'll explain. First thing, a proper evacuated tube was taken, cathode was there, anode was there, an outlet was made for the light rays to strike, so that then the electrons went, and this was properly connected. Yes, microampere ammeter was also connected. Voltmeter was also there. Rheostat was connected. Key, battery, everything was connected in the setup. In the setup. Key, battery, everything was connected. So when the light rays strike, the electrons moved. But as soon as you observed that, yes, electrons moved. So they thought to just change certain values. They increase they increase the intensity. See, here the photoelectric current will come. Photoelectric current. Here the photoelectric current will come. This will be observed. Now see class, when the graph was plotted between intensity and the photoelectric emission, so this is photoelectric current, and here you have intensity. So how was the experiment observed? It was observed by just changing the values of intensity. As I'm saying, this is done experimentally. So it was observed as soon as you increase the value of photoelectric current, intensity increases. Now you increase intensity, photoelectric current increases. You increase intensity and so on. This keeps on increasing proportionally. So it means you can say photoelectric current is directly proportional to the intensity. This is directly proportional to it. The current is directly proportional to the intensity. Fine. This was the first observation that was done. That effect of intensity, number of photoelectrons that are emitted per second, they're directly proportional to the intensity. It means if you increase the intensity, amount of electrons, ejection of electrons will become more. Electrons will keep on increasing. Second fact. See, potential. Now, here, when we are discussing effect of potential, a term comes from potential, that is stopping potential. Stopping potential, you can say. Cut-off potential, you can say. Stopping potential is there. Cut-off potential is also there. Now, see, as we have discussed that certain criteria are required by the electron to get fulfilled for the electron to become a properly free electron and perform the work in conduction of electricity and everything. So we had to have a specific value of wavelength. We had to have a very, very specific value of frequency, which has to be crossed so that photoelectrons can get emitted. Similarly, there has to be a certain threshold potential for which after that the electrons get emitted and the photoelectric effect goes into its action. But this stopping potential, this is a retarding potential. It means this is negative. Always you will see this is written as minus V naught. This is always written as negative. So it's the retarding potential. Because why? Because photoelectric current becomes zero. When the value of current becomes zero, no, potential becomes negative. So that's why it is written as retarding potential or stopping potential or cutoff potential. So stopping potential is what? If you see the definition of this, so the value of retarding potential, it means the negative potential. And when is the potential negative in the graph? It is when the photoelectric current becomes zero, at which photoelectric this becomes zero. This is called stopping potential. This is known as stopping potential for a given frequency. For a given frequency of incident. So this potential's value also has to be crossed. This potential value also has to be crossed for achieving a certain value. So at stopping potential, no photoelectrons are emitted. So the work done by the stopping potential on fastest electron is actually its kinetic energy. I'll tell you that, but let me just tell you how the graph looks like of theory part that I've written. C class. For a certain intensity, no. At this point, photoelectric current can be zero on the x-axis only, because this is the graph between photoelectric current and the potential, stopping potential. So see, for us, when the photoelectric current becomes zero, it is either possible on this axis, either it is possible on this axis or on this axis. See, if we plot it here, it will give you positive answer, right? So we have to, because we know retarding potential is negative and it can only be zero at some point over here. So the graph that you obtain, this graph comes as it is to draw. At some intensity, I1 you have it. Now let's do what? Let's increase the intensity. So when you increase the intensity, stopping potential's value will remain fixed. It's just that intensity of the current will increase. Even if you increase it more, stopping potential's value will remain the same, but intensity will increase. This point that you're obtaining, minus V0, this is stopping potential. This is stopping potential. So it means I3 is greater than I2 is greater than I1. These are in their descending orders. So if you apply a negative potential at any point, let's say that plate A and C, that we are taken in the diagram, and increase the magnitude gradually, it is seen that photoelectric current decreases rapidly until it becomes zero. All right, until it becomes zero for a certain value of negative potential. And for a given in frequency of incident radiation, photoelectrons are emitted with all velocities ranging from potential with no photoelectrons are emitted. So work done also you can calculate kinetic energy, we'll see. But main graph that is important is here. And definition I am repeating one last time. The value of retarding potential at which the photoelectric current will become zero. This is known as cutoff potential or what? Stopping potential. Now, C class, the graph is fixed. This is the anode potential actually. This potential, this is anode's potential. So when yes, I was saying when variation of photoelectric current comes with anode potential, or if it just comes with a potential, plot this graph. Yes, I was saying that this gets converted into kinetic energy. See, kinetic energy maximum value will be half m v maximum square. One more conversion is there. One more thing is there. Electronic charge multiplied by stopping potential. Electronic charge multiplied by stopping potential. So you can write it as EV naught, or you can write it as half mv square. We'll discuss this. We'll discuss this more. One last thing is left. Let me tell you that also, effect of frequency, because effect of frequency is not difficult. Effect of frequency is there. See, whenever you have to study the effect of photoelectric current, no, effect of frequency on it. Intensity radiation at each of the frequencies is initially adjusted in such a manner that a current flows same in all the slots that you have. Current should flow same in the positive potential. So potential with a plate, one you can say, or A and C I wrote it, no, it gets reduced to 0, and negative direction it increases. I'll show you the graph. See, if you have frequencies, no, even if you increase the frequencies, even if you're increasing the frequencies, greater potential is then required to stop it. Understood? It means for a larger amount of frequency, you're getting the same current. For a smaller amount of frequency, you're getting the same current. I'll show you with the help of graph. C class. Let's say this is some frequency 1 and a current is obtained. Now, even if you increase the frequency, no, this will reach this point of the graph only, even if you have frequency 2. For frequency 3 also, this will have the same value. So this part of current that we are obtaining when we are plotting photoelectric current versus frequency, this is known as saturation current, for which no value is getting increased. So this is nu 3. And if you want to know, see, I have written in the increasing order. It means nu 3 is greater, nu 3 greater than nu 1. This is the order of it. All right, this is the order of it. It means at different values of frequencies. Firstly, you should note this fact as well. Here, what do we get? We get stopping potential 1, stopping potential 2. Remember, we had stopping potential. Here also stopping potential 3. So values of stopping potential increases when the frequency increases. All right. Frequency increases. So stopping potential also increases. So frequency increases, stopping potential increases. So in physical terms, you can just understand that maximum kinetic energy is required. So this graph was, these three graphs were there, especially intensity and frequency graph come a lot in exam. Note down this point, note down all these points. This you have done from here. Class, one thing I wanted to ask you, apart from your refraction test that you had, did we have any other test, any test paper that is left pending for all of yours batch? All those who have appeared for the test. I think last was that refraction test only. After it, we didn't have any test. If you all have any pending papers, let me know. I think that is the last one only. On 1st of November, which we had. If you all by chance know, I'll share the score of refraction again once. If by chance you all have your pending papers, then let me know. I'll cross check it and I'll send you your score. But I think in this batch, no papers are pending. All the tests were covered, no? See, after EM waves for reflection, we had the test, then we had the test for refraction, and then we were supposed to have the test for interference today. This was the procedure. Fine. So 22nd, we'll have it. Rest of you, let me know if anyone sees the paper is unchecked, please let me know. I'll stop you today. I think this is enough for today's class. Photoelectric effect, some topics are left, and de Broglie's hypothesis. I just have to confirm whether de Broglie's is included or not. I'll share. And then I've received your email ID. So after the class, I'll try to share the link of ray optics with you. All right, class. So all those who have completed, you all can leave. We'll meet on now Tuesday. Okay. Thank you so much, class.
Thank you, teacher.
Thank you, ma'am.
Thank you, ma'am.